We have seen that the periodogram gives us a spectrum estimate with high variance and high spectral leakage, but otherwise with good resolution. And we've seen that we can use a modifier or a windowed periodogram in order to reduce the spectral leakage at the expense of some of this resolution. However, none of these methods address the variance of the estimate, so this is what we'll look at now. So let's begin by considering the concept of periodogram averaging. So what we previously assumed was that we had a block of samples from a process, so we had capital N samples, and these were the basis for our estimate, be it the periodogram or the modified periodogram. However, if it were the case that we had capital K such blocks of data, what we could do is we could compute an estimate of the power spectral density from each of the blocks, but then we could take all of these estimates and create an even more reliable estimate by taking the average of the individual estimates. And one can show that if these blocks are independently drawn from the process, then the variance of this improved estimate will only be a factor of 1 over k times the variance of any individual estimate. And since the variance of the periodogram and also the modified periodogram is proportional to the squared power spectral density of the original process, the variance of this new and improved estimate would only be 1 over k times the original power spectral density squared. So in particular, if you choose the number of blocks very large, or if you have access to a large number of data blocks, you could create an estimate with a variance which is very small. And this is also what was done in order to create the numerical examples where we showed the ensemble average of the periodogram estimate. So in that case, several periodogram estimates were computed, and we took the average and plotted that. However, for a particular case, we of course don't have access to capital K blocks, so we're given capital N samples, and we have to do as well as we can with these capital N samples. So this is the problem of the spectrum estimation. But we can still use the concept of periodogram averaging. So the way to use this concept is to take our N samples and you divide it into K blocks of length L, where L is smaller than N. And this gives rise to a method called Bartlett's method for estimating the power spectral density. So in Bartlett method, you would choose the indices K and L so that K times L is equal to the number of samples, or at least less than the number of samples. Then you would create K blocks of length L from the original data. You compute for each of these blocks a periodogram estimate, and then you average these in order to get your final estimate of the power spectral density. And the idea here is that this estimate will have a lower variance than if you would have computed the periodogram for the entire data block, since that would have involved no averaging at all. However, Bartlett's method can reduce the variance by a factor of k, which is good, but there is a price to pay for this. So what do you think the price is if you apply Bartlett's method? So do you think the side lobe levels of the estimate will increase by a factor of k? Or do you think that the side lobe levels will increase by a factor of L? Or will you have a resolution which is decreased by a factor of k, or a resolution which is decreased by a factor of L? Or don't you think there is any significant penalty to be paid by choosing Bartlett's method over the periodogram method? Well, the correct answer is option number 3. So the resolution would be decreased by a factor of k. And this is because we are now using length L blocks. And for the periodogram based on the entire data, we would have a length N block. So since the resolution depends on the length of the block, which we saw how this affects the windows, since we're now using a length L block, instead we have a decrease in the number or in the resolution by a factor of N over L, which is equal to k in this case. So we can exemplify this using the AR4 process that we used before in order to exemplify spectral estimators. So this process has a power spectral density given by the black curve. And if we do a periodogram estimate based on 256 samples for this process, it could look something like this. So different realizations of this process and estimate would lead to different estimates, and the amount of up and down for any particular point of the estimate would be quite large, since the periodogram has a large variance. So you can create estimates which are consistently closer to the true power spectral density by using Bartlett's method here. So in this particular case, we would still use 256 samples, but we could divide them into, say, blocks of length 64, in which case we would have 4 blocks to average over. So if we do that, we see that we have an estimate which is overall closer to the true power spectrum. And we will also see that if we draw several more realizations of this process, the amount of variation between realizations would be reduced. So we should have a variance which is only a factor of 1/4 of the variance of the periodogram, since we have k equal to 4 blocks to average over. And now in Bartlett's method, if you obtained more samples, so if we increase the number of samples that we had access to from 256 up to 1024, we could use those in several different ways. So either we could use them to increase the resolution of our estimate by increasing the length of each block, or we could use it to decrease the variance by increasing the number of blocks, keeping the length of each such block fixed. So let's assume that we do that. So we increase the number of blocks from 4 to 16. So we still use a data number or data length of 1024, still keeping the blocks the same but increasing number of blocks. And what we see now is that the variation between different realizations would even be further reduced. And in this particular case, it turns out that the deviation of the estimate from the true power spectral density has more to do with spectral leakage rather than variance of the estimator. And we can of course address that using modified periodograms instead of periodograms, as we saw before. If we change the periodogram built into Bartlett's method by a modified periodogram, what would happen is that we would take each of these blocks of data that we cut out of our total set of data, and we would multiply it with a smooth window before computing the Fourier transform and building the modified estimate. However, one can argue that this is an inefficient use of data, because data close to the borders of the blocks would get multiplied by a small number. So in effect, we're not using as much of that data as we could. So if you choose to use a smooth window like this in Bartlett's method, what you could in fact do is to create an increased number of blocks and let them partially overlap and apply a window to each of these data. So each of these blocks would not be as informative as it would be dependent or statistically dependent on the previous block, since you have this overlap. But you would get an increased number of blocks by doing this partial overlap, and that would overall lead to a reduced variance. And this is the basis of a method called Welch method. So in Welch method, we would choose 3 parameters instead of 2. So you would choose k, the number of blocks, you would choose L, the length of each block, and you would choose a factor d, which models the overlap between blocks. So k times L, so the number of blocks times the block length, would in this case be equal to or strictly greater than the samples, and this d parameter, which would explain the shift of each block, would be somewhere between the full length of a block and half the length of a block, allowing for at most 50% overlap. And then you would create these blocks by taking overlapped portions of the data, and again create an average estimator by taking the average of these length L modified periodograms, and you get an estimator which would look like this, where U again is this factor based on the window in order to account for an absolute value of the window. If we look at that numerically, returning to the last example with Bartlett's method applied to a data length of 1024 data samples divided into length 64 blocks, so we get 16 blocks. If we used Welch method with 50% overlap, we would instead of 16 blocks get a total of 31 blocks. And in this particular case, we applied the Hamming window to the data when we overlap the blocks. So this will have 2 effects. So first of all, the variance will be reduced from what we saw in Bartlett's method. Also, because we're using a window to the data, we will at the same time reduce the spectral leakage. So the deviation between the estimated power spectrum and the true power spectrum in these regions where we have low power spectral density would be reduced by the fact that we use a window that reduces the spectral leakage. And since we have a larger number of blocks, we see that the variance between estimates or different realizations of the estimate would be reduced. So what we have done with Welch method is to create an estimator that's consistently more reliable for estimating the power spectral density and at any particular frequency. And we can now compare that to the estimate produced by the periodogram using the same amount of data, so in this case 1024 samples. So here you see the Welch estimate in red and the periodogram estimate in blue. And what we can see is that the Welch estimate for any particular frequency, it will be consistently closer to the true power spectrum than the periodogram estimate will be. So the price that we pay for this is that we have a decreased resolution of the estimator. So at any particular point where the true power spectral density has these sharps peak, we wouldn't be able to capture them as well using this lower resolution method, where the lower resolution is caused by the fact that we apply a rather short window with a wide main side lobe, causing the decrease in the 3 dB bandwidth of that window and a reduction in the resolution of the estimate. However, for this particular process, it's easy to argue that Welch method is superior to the periodogram in terms of accurately estimating the power spectral density. Still, once you have plotted the periodogram estimate like this, you can see that even though the periodogram estimate has a large variance, some of the points will be above the true power spectral density and some of the points will be below. So if you want to get an accurate estimate of the power spectral density at some frequency, what one can also do is to average the periodogram over frequencies within some narrow range around the frequency of interest. And this is the basis of a method called Blackman Tukey's method. So what Blackman Tukey's method would do is it would take the periodogram estimate and it would convolve it with a smoothing function performing this averaging property in the frequency domain. However, this is not how you need to implement it, so you can implement it in the time domain. So since we know that the periodogram estimate is the Fourier transform or the discrete time Fourier transform of an autocorrelation estimate, we could use lowercase w of k in order to denote the inverse of this smoothing function and apply that as a window to our autocorrelation function estimate. And it makes sense a priori to window the autocorrelation function estimate, since we know that the estimate is less reliable for larger time lags, since it's based on an average with not as many terms for larger time lags. So by weighing down values of the autocorrelation estimate for large time lags, it stands to reason that we could improve the estimate, and this is equivalent then to the averaging in the frequency domain, which would reduce the amount of variation in the final estimate. So in order to get this to work, W of k needs to satisfy some property. So typically you would want this to be symmetric so that W of nu here is a purely real valued function. It also makes sense to make this windowing function identically equal to 0 for large time lags, so time lags above some capital M. And this would be equivalent to throwing away the most unreliable estimates of the autocorrelation function. And there are also some other restrictions having to do with the fact that you want this function to be purely positive so that the estimator never produces a negative power estimate for any particular frequency. But having done all of that, you could implement the estimator efficiently or computationally efficiently by computing first the estimate of the autocorrelation function for the entire data, and then taking this window, apply it to the data, and use the fast Fourier transform in order to evaluate this discrete time Fourier transform at a given set of frequencies, nu k, where k goes from 0 to n-1, and where n here is the length of the FFT that you apply in order to evaluate this numerically at certain frequencies. Assume now that you use this idea of using the FFT algorithm to compute or evaluate different values of the Blackman Tukey estimate at different frequencies. And if we assume that the Blackman Tukey estimate has a time lag of m, what's the smallest or shortest length of the FFT that you could use in order to correctly evaluate the Blackman Tukey estimate at these different frequencies? So would the length of the FFT have to be greater than the time lag? Would it have to be greater than or equal to 2 times the time lag, greater than or equal to 2 times the time lag plus 1, or does it actually have to be greater than or equal to the time lag squared? The correct answer to the question is option number 3, so it has to be greater than 2 times the time lag plus 1. And the way to see that is that we're computing or evaluating a discrete time Fourier transform of a sequence which has length 2m plus 1. So these are all the values where the sequence could be non-zero if we apply a maximum time lag of m. So our FFT has to be at least this long in order not to suffer from the circular convolution properties of the FFT. In this example, we have computed the Blackman Tukey method with a maximum time lag of 64 samples for the same example that we considered before, and we used the Blackman window in order to window the autocorrelation estimate. And what we can see is that we get an estimate here in red which quite accurately captures the true power spectral density of our AR2 process that we try to estimate the power spectral density of. And if we consider different realizations, we see that the variance of this method has also been reduced from what we experienced in the periodogram estimate by averaging over different frequency values. And also the Blackman Tukey method, we could change the parameters that we use. So for instance, we could reduce the maximum time lag from 64 samples down to 32 samples, so we could halve it, and that would reduce the variance even further at the expense of the resolution of the method. So we would see that we get an increase in the main lobes of the window that we apply. So each spectral peak here would be widened, but we would see a reduction in the amount of spectral leakage that we have in the estimator. We can now summarize all of the properties of the estimators that we've considered in this lecture. So all of the estimators will have properties in terms of variance, bias, and the bias will influence the resolution of the estimator. So for the periodogram and the modified periodogram, one of the key properties is that the variance doesn't decrease with an increasing number of samples. So collecting more data doesn't lead to more reliable estimates, although we have a higher precision in the estimates. For Bartlett and Welch method, if you keep the block length fixed, the variance of the estimator will tend to 0 as 1 over the number of data samples. The same is true for Blackman Tukey if you have a fixed time length for the window and you choose a particular window for the estimator. As you collect more data, the variance will decrease as 1 over n. In terms of the bias, we'll have that the periodogram, the modified periodogram, Bartlett and Welch will have a bias which is explained by a convolution with a true power spectral density with this window function. So the length of the window function in the time domain will determine the spectral properties of the bias term here, and also the resolution. So for the periodogram and the modified periodogram, the resolution will be 1 over the number of samples times some proportionality constant, which is 0.89 in case of the rectangular window, and dependent on the window in terms of the modified periodogram. For Bartlett and Welch, we have the same properties, but here you have to remember that the length of the window that we apply is shorter than for the periodogram and the modified periodogram, since we apply it per block. For Blackman Tukey, one can also show that the resolution is inversely proportional to the time lag that you choose for the window. So to summarize, in this last video we saw several non-parametric spectrum estimation methods that traded resolution for an improved variance of the estimator. So in Bartlett and Welch method, this was accomplished by taking the full set of data and dividing it into blocks, which are then averaged. And for each such block you would implement a periodogram or a modified periodogram, depending on if you use Bartlett or Welch method. So Bartlett is a little bit simpler to implement and think of conceptually, but Welch is typically the one to choose because the performance is better for the same amount of data. Then we also saw that you could achieve a lower variance by smoothing the periodogram in the frequency domain, and this was the key idea behind the Blackman Tukey method, which also traded resolution for an improved variance of the estimator.